Hello everyone! In this video I'm going to demonstrate how teachers and students can easily model and control dynamic systems through cross-simulation between multi-body and 1D block softwares. We are going to highlight some challenges regarding to modeling dynamic systems and how co-simulation between different platforms, in this case multi-body and 1D, reduces modeling time and ensure better results. First of all, with a co-simulation, it is possible to explore and improve engineering skills in different model levels, since 0D, 1D to 3D. Furthermore, model a dynamic systems on a multi-bar environment provides a high-fidelity level system, and that approach can be considerably simplified by using multi-body models. Finally, it is possible to easily evaluate multiple control parameters to deliver a more assertive configuration for the system. As mentioned, there are some challenges in modeling dynamic systems, like reduce a complex mechanical system to a mathematical representation, choose the level of detail and choice of idealization of components, achieve speed in change parameters, seeking the best system response. And we will see how a co-simulation using Altair products can deliver good solution to these challenges. Now that we know what is a co-simulation and its goals, I will demonstrate you how it works using a very known engineering model, that is the ball beam system. Basically, that system is composed by four bodies: the motor, the bar, the beam, and the ball. The goal of this model is controlling the ball position by the motor theta angle, as shown in this picture. So, to solve this system, the 3D model will be modeled on a multi-body software, and then that model will be the plant of our 1D control model, based on block diagrams. Regarding to our main multi-body platform, where dynamic systems are modeled, we will use MotionView and MotionSolve. With them, we can simulate any mechanical systems predicting force, kinematics, and even dynamics of the motion. Being able to solve mechanical systems with rigid, flexible bodies that are connected by different types of kinematics constraints and flexible connectors. So here we have the steps to model a system on a multi-body environment. We would have to create some entities like points and then bodies, create the desired joints to connect the bodies, create the type of motion that will be imposed to the system, create the contact between the bodies, and set the system input and output variables, create the desired measure to post-processing, and finally set the solver settings and export the XML file. So let's move on to MotionView and understand them. So here we have the MotionView. First of all, it is important to keep in mind that in order to create bodies and later attribute their properties as mass, center of gravity, and inertia, it is necessary to create points to those bodies be referenced. Thus, from the 2D or even 3D sketch, it is important to know the component's dimensions to create the points. As you can see in this model, some points were created, thus the body creation could be done. In the motion view, it is possible to create some types of geometry graphics to associate them with the bodies. Once this model is composed by simple geometry bodies, all components can be created in the interface itself, because they are cylinders, balls, and boxes. Otherwise, it is possible to select a CAD geometry as well. Once we have the created bodies, it is possible to associate their properties or select to calculate automatically from the geometry graph created. Now that the points and bodies have been created, you can notice that the setup will be very easy. At this moment, joints should be created to connect the bodies. To create them, just select the bodies, the point of origin, and the axis to which is aligned. There are several possibilities of restriction to use in MotionView, like force, torques, velocity, but in this problem itself, a displacement motion was used. In this case, is theta displacement of the motor, which will be used to control the ball position. Finally, if there is contact between the components, it should be added. And as you can see, there are some parameters that can be changed, such as stiffness, damping, friction, and etc. After all these setups, our model is almost ready. Now the input and output variables must be created so that when exporting this model as a block, the 1D model would have variables to control. In solver variables, you will only create the symbolic variable. And in solver array, you will indicate which will be the input and output of the plant. Finally, the value of the motion variable must be referenced to the input variable, since the set point will come from the 1D model. For post-processing purpose, it is possible to create several measures to evaluate the movement of bodies. In this case, I want to evaluate the ball position, so I create a measure for that. Finally, as last step, you can set your run settings, like the end time, print interval, or even the maximum step size, depending on your frequencies. Once you have them set, you should export your XML file, and then the motion view model will be done. In terms of our main 1D platform software, we will use Activate, that is an open integration platform for multidisciplinary system simulation. With it, we are able to easily model dynamic systems, both continuous and discrete, and their controls using a graphical language. As you can see in this first figure, Activate is a complete integration tool working since signal and physical blocks, doing co-simulation as discussed in this video, and also handling with FMU environments. To easily illustrate you how is the logic behind this kind of tool, here you have an equation based on symbolic language, and below, how could this be represented on Activate by blocks. In terms of Activate workflow, these are the steps to model a simple control system. So you should create your input, your sum block, your control for sure, your plant, that in this case will be our 3D model set on motion view, the scope block to analyze the results, and set your model parameters and solver settings, and finally run. So let's move on to Activate. As mentioned, the 1D diagram block modeling can be started by the input signal. On Activate, there are a wide option of it on signal generators. On this model, the signal generator block was chosen due to its flexibility to set different desired ball position, that is the set point of the system. Later, the sun diagram should be selected, and it can be selected on math operations. So now, the control implant should be set. Regarding the control, it was used a PID block that can be selected on dynamical, and its parameters were set by symbolic variables that later will have their numerical values. As you can see in this model, some unit conversion blocks were used and then can be selected on signal conversion. But actually, it depends on how you work with your signals in their units. Now, on the plant we have the key capability. Instead of modeling the system on a time or even frequency domain, a MotionSolve block that can be selected on consimulation will be used. That block basically imports the previously discussed model and it will be ready to be used once the input and output parameters have already been set on motion view approach. Furthermore, in order to get a more realistic model and avoid high-frequency signals, a low-pass filter was used, giving a high-level model fidelity. Finally, a scope block should be included. That can be selected on signal viewers, and it will be used to compare the set point and plane's outputs to see how the control is working. As mentioned, some model parameters were set as symbolic variables, and to set the values, you should go on model icon. Now your model is ready. Set your solver settings on this icon and run. As you could see, the ball is really going to the desired position, respecting the control parameters. By the way, I would like to mention that many techniques can be used to calculate the control parameters. In this case, I've used a simple PDF for teaching purposes. Finally, you can find the model used in this presentation on Model-Based Development Forum. By the way, feel free to ask anything about our solution there. It will be a pleasure to help you. And I also would like to invite you all to share with us your achievements in Altair community. Many thanks for your attention. Bye.